Hey everyone, and welcome. Today, we're diving into a topic that, on the surface, can seem a bit intimidating: fluid mechanics. We're going to explore what I like to call the master secrets of fluid mechanics. By secrets, I don't mean hidden formulas or magic tricks. Instead, we'll be focusing on the key concepts that, once you really understand them, make the rest of the subject fall into place. It's about shifting your perspective. Our goals today are to demystify complex fluid problems by introducing a few powerful and universally applicable principles. You'll learn to see problems not as collections of equations, but as stories of energy and flow, allowing you to solve problems you might never have thought possible. Think of it like learning to cook. You can follow a recipe, but a great chef understands the underlying principles of flavor, heat, and texture. That's what we're going for here. Let's get started. Our first big idea is to think of a problem not as what is the answer, but as how is the energy moving and changing. This is the foundation of the first law of thermodynamics. And in fluids, it's expressed by the famous Bernoulli's equation. Bernoulli's principle states that for an incompressible, inviscid, steady flow, a change in velocity causes a change in pressure. More generally, it describes the conservation of energy. This means that the total energy in a fluid's flow is constant. That energy can take different forms: pressure, kinetic energy from its speed, and potential energy from its height. Bernoulli's equation looks like this. Let's break it down. P is the static pressure. 1/2 rho v squared is the kinetic energy term, related to the fluid's motion. And GEH is the potential energy term, related to the fluid's height. The secret here is that you don't need to know all these terms. You just need to know that their sum is constant along a streamline. So, if the fluid speeds up, the pressure has to drop. If it moves higher, something else has to give. Think about it like this. Imagine a car driving on a level road. Its total energy is its speed. Now, it starts to go up a hill. It gains potential energy, so to keep its total energy the same, it has to lose kinetic energy. It slows down. Fluids do the same thing, just with pressure as another form of energy. Let's put this into practice with a classic example. Imagine a large water tank with a small hole in its side near the bottom. We want to know how fast the water exits the hole. This is called Torricelli's law. Let's call the surface of the water point 1 and the hole point 2. We can set up Bernoulli's equation between these 2 points. The total energy at point 1 must equal the total energy at point 2. Now for the magic. We make some assumptions, which is often how you simplify complex problems. We assume the tank is large, so the water level drops very slowly. This means the velocity at the surface, v1, is essentially 0. So we can cross out the kinetic term at point 1. Also, both the surface and the hole are open to the atmosphere, so the pressure at both points is the same, atmospheric pressure. We can cross out the pressure terms on both sides. We can also set our height reference. Let's say h2 is 0 at the hole. This simplifies the equation dramatically. What we're left with is rho GH equals 1/2 rho v squared. The fluid density rho cancels out. Solving for v2, we find the exit velocity is the square root of 2gh, which is Torricelli's law. It's the same speed an object would have if it fell from rest from that same height. All just by applying the principle of energy conservation. Let's move on to our second big idea. What happens when a fluid flows through a pipe that changes diameter? This brings us to another fundamental principle: the conservation of mass. For an incompressible fluid, the mass flow rate must be the same at every point in the pipe. Think of it like a traffic jam. If 4 lanes of traffic suddenly merge into 2, the same number of cars are trying to get through the narrower section, so they have to speed up. Water works the same way. The equation for this is A times V equals a constant, where A is the cross-sectional area of the pipe and V is the average velocity of the fluid. So, if the area A decreases, the velocity V must increase to keep the product AV constant. This is a powerful, intuitive tool. For a circular pipe, the area is PR squared, which is proportional to the diameter squared. That means if you cut the diameter in half, the area shrinks by a factor of 4. To maintain continuity, the velocity has to jump by a factor of 4. It also works in reverse. A diver entering the water makes a big splash because their body displaces the water in a small area, forcing it to move very quickly in other directions. Let's bring our two principles together with another classic device, the Venturi meter. A Venturi meter is a pipe that narrows in the middle. We're going to use it to measure the flow rate of an incompressible fluid. Let's call the wide section point 1 and the narrow section, or throat, point 2. Our goal is to find the velocity of the fluid at point 1 using only the properties of the meter and the height difference measured by a U-tube manometer. First, let's use the continuity equation between point 1 and point 2. Since the mass flow rate is constant, the product of area and velocity at point 1 equals the product at point 2. This gives us a relationship between V1 and V2. Next, let's apply Bernoulli's equation between the same 2 points. Assuming the pipe is horizontal, the heights are the same, so the h terms cancel out. We're left with the pressure terms and the kinetic terms. Our manometer measures the pressure difference, P1 minus P2. Using our continuity relationship, we can substitute V2 in the Bernoulli equation. It's a bit of algebra, but the idea is simple. One equation links the velocities, the other links the pressures, and we combine them. After some rearrangement, we get this formula. All we need to measure are the 2 areas and the pressure difference, which the manometer gives us, and we can calculate the flow velocity. It's a beautiful application of our 2 master principles working together. So far, our fluid secrets have been about things that don't change, energy and mass. But in the real world, things change. This leads to our third master secret. The third secret is to always ask yourself, is the flow steady or unsteady? This is often the first question you should ask when looking at any fluid problem. A steady flow is one where the velocity at any given point in space does not change with time. Think of water flowing smoothly from a hose. An unsteady flow is the opposite. The velocity at a point changes with time. A gust of wind, a beating heart, or the waves on a beach are all unsteady. Why is this distinction so important? Because almost all the simple formulas we learn, like Bernoulli's equation and the continuity equation, are only valid for steady flows. In an unsteady flow, we need to consider acceleration. F equals ma is still true, but now it's not just the force from pressure gradients. It's also the force needed to accelerate the fluid. This introduces a whole new set of terms. For unsteady flows, we need the full Navier-Stokes equations, which are much more complex. The secret is to recognize when you're in unsteady territory, so you know you need to think beyond the basics. Let's look at a simple example that can fool you if you don't consider unsteadiness. Imagine a U-tube filled with water. If we push the water down on one side and release it, what happens? The water oscillates up and down. This is clearly unsteady. The velocity at any point in the tube is constantly changing direction. A common mistake would be to try and apply the steady Bernoulli equation. You might say the pressures at the 2 surfaces are the same, atmospheric, and the velocities at the extremes are 0. Bernoulli's would suggest that the water level should be the same on both sides at the start and end, but we clearly see an oscillation. The secret is to recognize the unsteadiness and account for the inertia of the fluid. The energy is constantly converting between potential energy, the difference in height, and kinetic energy, the motion of the water. This is simple harmonic motion. The forces at play are not just pressure. They include the force required to accelerate the mass of water in the tube. This is a classic unsteady problem, and ignoring that fact will lead to the wrong answer. We've talked about energy, mass, and steady versus unsteady. But what about the elephant in the room? What about friction? In fluid dynamics, we call this viscosity. This brings us to our final master secret. Is the flow viscous or inviscid? In other words, is friction important? Viscosity is a fluid's resistance to flow. Honey is very viscous, water is less so, and air is even less. The key is that real fluids have viscosity. It's a property of the fluid itself. Why do our simple formulas ignore it? Because accounting for it is complicated. Viscosity creates shear stress, and it converts mechanical energy into heat, causing pressure losses in pipes. But here's the secret. For many problems, especially in aerodynamics, we can get a fantastic approximation by ignoring viscosity almost everywhere in the flow. We call this the inviscid assumption. But it's crucial to know that the inviscid assumption breaks down in a very specific thin region right next to a solid surface. This region is called the boundary layer. In the boundary layer, viscosity dominates. The fluid goes from having zero velocity right at the surface to its full inviscid velocity just a millimeter or two away. Inside the boundary layer, you need the full Navier-Stokes equations. Outside it, you can often use the simpler equations, like Bernoulli's. This idea of the boundary layer is the secret to understanding how wings generate lift. Let's look at the famous top surface speeds up explanation. This explanation suggests that air flows over the curved top surface of a wing faster than the flat bottom. According to Bernoulli's principle, this higher speed causes lower pressure, creating lift. While this isn't the full picture of lift, it's a great example of the boundary layer secret. Why does the air speed up over the top surface? Because the streamlines are crowded together there. Remember the continuity equation? A times V is constant. The boundary layer makes the effective area for the flow smaller on the top. The top surface has a boundary layer, but it also has a thicker displacement thickness effect, which pinches the flow, causing it to accelerate. The air speeds up outside the boundary layer. Viscosity is creating the effect by forming the boundary layer, but the lift itself is generated by the inviscid pressure difference that results. You can't have one without the other. Let's summarize our master secrets. These are the lens through which you should view every fluid mechanics problem. First, always ask about energy. You can almost always use Bernoulli's equation as long as it's for a steady, inviscid flow. Second, consider mass flow. The continuity equation is always true for incompressible flow. Third is the flow steady or unsteady. This determines which equations you can use. Fourth, is viscosity important? It always is near surfaces, creating a boundary layer, but can often be ignored elsewhere. By asking these 4 simple questions at the start of any problem, you'll be able to identify the correct approach, make appropriate assumptions, and solve problems that might have seemed impossible before. So next time you're faced with a fluid problem, don't just reach for a formula. Take a step back. Ask the questions. Become a master of fluid mechanics. Okay. Let's try a practice problem to solidify these ideas. Imagine a large pipe of diameter d with water flowing at velocity phi. The pipe suddenly narrows to a diameter of d. We want to find the pressure difference between the two sections. First secret, energy. This looks like a perfect Bernoulli's equation problem. The pipe is horizontal, so the height term cancels out. We can write the equation like this. Second secret, mass flow. The continuity equation must hold. Area 1 times V1 equals area 2 times V2. Since area is P times the radius squared, or pi d squared over 4, we can say that V2 is V1 times the ratio of the areas, or V1 times the ratio of the diameters squared. The fluid must speed up. Now we substitute V2 into our Bernoulli equation. We get P1 plus 1/2 rho V squared equals P2 plus 1/2 rho times our new velocity expression squared. Finally, we want the pressure difference, P1 minus P2. We rearrange the terms, and here is our solution. The pressure difference is proportional to the fluid density and the square of its original velocity. But the key factor is the ratio of the diameters. This makes perfect sense. The bigger the change in area, the bigger the change in velocity, and thus the bigger the pressure drop. By applying our secrets step by step, we've solved the problem. Let's try one more practice question. This one is a bit more conceptual. This is a common exam trick question. Imagine water flowing through a horizontal pipe. At one point, there is a small obstruction that partially blocks the flow. Does the water pressure just before the obstruction increase, decrease, or stay the same? Take a moment to think about it. Is your intuition saying the pressure should build up behind the obstruction? That's a very common but incorrect answer. This problem is about the boundary layer. When the fluid encounters the obstruction, the flow streamlines are forced to crowd together to go around it. This is exactly like the situation on top of an airfoil. The crowding of the streamlines effectively narrows the passage, increasing the local velocity due to the continuity equation. And we know from Bernoulli's equation that when the velocity increases, the pressure must drop. So the pressure just before the obstruction actually decreases. The secret here was recognizing the local acceleration and applying Bernoulli's principle. Let's quickly recap what we've learned. Our mission was to demystify fluid mechanics. We did this by focusing on 4 master secrets: the principles of energy conservation, Bernoulli; mass conservation, continuity; the importance of steady versus unsteady flow; and the critical role of viscosity and the boundary layer. You now have a powerful framework for analyzing any fluid problem. Don't just follow formulas. Question the assumptions behind them. Look for the underlying physics. This method will help you build your physical intuition and confidence. You're no longer just solving problems, you're understanding them. Thank you for watching, and good luck on your fluid mechanics journey.